Hello everyone, good evening. Thank you all for being here. I really appreciate everyone coming.
You too.
Thanks, Martin. Welcome to my final presentation over organometallic chemistry. So what we're going to do tonight is first talk about ISM and quickly recognize my two mentors and my supervisors, then go over some of the research I did earlier on in the year. Then I'm going to talk about the significance of the topic and of my product, and then I'm going to talk about the product itself. So first, here's a Mr. Ryloff mandated quote. This really just helped me get through hard times in ISM. A lot of the times I would be researching and I'd go down a rabbit hole that led nowhere. And this kind of just told me to keep on going because there's this at the end of the year to look forward to. So let's talk about ISM real quick. There were three main reasons why I took ISM. First of all, I really wanted to take organic chemistry, but unfortunately, Prescribed ISD does not offer organic chemistry. So I took the opportunity to learn as much as I could this year in ISM before I go off to college. Second, I really wanted to know more about what kind of jobs you could get as a chemist and what a day in the life of those jobs would look like. And thirdly, I knew that this year would be the perfect opportunity to get my name out there and to make connections in the field. So this is my topic. It's organometallic chemistry, and that's a pretty big word. Let me break it down for you. So organic chemistry is the study of chemistry. It's these long carbon chain bonds. You can think of like human beings or anything made out of carbon. And so when you add metals into the mix, you get organometallic chemistry. So there's a metal, so that's an organometallic compound. So this topic digs into really advanced bond theory due to the nature of transition metals, and it also delves into some really awesome and niche topics from inorganic and coordination chemistry. So here's some stuff I did earlier on the year before my original work and my final product. These are two interviews I did. First of all, this is Dr. Tracy Benson. He is Mr. Taylor's friend at Lamar University. He taught me that I need to specialize in my topic. So earlier on in the year, I had a very broad scope, and through him, I learned that I really needed to pare that down into something that I could research specifically. And then this is Dr. Stephen Gonzalez. He works at Collin College, and he taught me the importance of networking. So prior to that, I had an interview with my mentor, Dr. Tombar, and I mentioned him in the interview, and we had a cool conversation because he happened to know of him, and we got into his job at, he used to work at a pharmaceutical company researching. So here are my two mentors. First of all, this is Dr. Tombar. He is here today. Give him a round of applause. He helped me tremendously. He helped me write my original work, and he was very pivotal in teaching me organic chemistry and teaching me reaction mechanisms. I'm very grateful that he was my mentor and that he's here tonight. He is the head of the organic chemistry department in UT Southwestern, and he is also the professor of biochemistry there. And his lab focuses on researching new reactions and molecules in relation to medicinal chemistry. This is my second mentor, Dr. Delaney. He really helped me because he allowed me to use his lab space to synthesize my final product. He is the UTD Assistant Professor of Chemistry and Biochemistry, and his lab focuses on saturated heterocycles to help the fields of agrochemistry and pharmaceuticals. So through my interview that I mentioned earlier with Dr. Tracy Benson, I learned that I need to specialize. So here are the three key steps that I took in order to specialize. So before I even took ISM, I watched a lot of YouTube videos that detailed a lot of really cool organic reactions. And through that, I knew that organic chemistry was something that I really wanted to try out. So in ISM, I bought a very pivotal textbook called Organometallics and Catalysis by Manfred Bachmann, and it enlightened me on a very cool molecule called ferrocene that we'll be talking about a lot later. So after that, I knew that I had to research it more in depth, and so I took a peek into academic journals, and these really taught me the synthesis and the applications of ferrocene-based anti-cancer medicines. So this is the molecule, this is ferrocene. So it's an organometallic compound, it's very special. You can think of it as an iron hamburger. So this is our patty, and then these two rings are buns. They're 5 carbon rings called cyclopentadiene. So it's remarkably stable as an organometallic, so it's very stable in air and in moisture, and it's very resistant to strong bases. And so that made it a very good potential for synthesis because I didn't know exactly how much equipment I'd have access to. So I knew I need something that would be air stable. So in terms of why this molecule is important, it has this very awesome ability to take a pre-existing medicine and improve its qualities. So for example, there's this anti-malarial medicine called chloroquine. So when you add a ferrocene group and replace part of the chloroquine, it creates ferroquine. And what this does is that it creates a medicine that is able to effectively target strains of malaria that are resistant to chloroquine. So another application of ferrocene is in glucose testing in diabetes. And finally, the application that I decided to research is in anti-cancers. So this is ferrocene flutamide, which was the subject of my original work, my semester project. And it essentially takes this pre-existing cancer molecule flutamide, and it replaces this group here with the ferrocene group. So this molecule essentially improves upon flutamide because it consistently inhibits cancer cell growth, whereas flutamide has this nasty side effect of proliferating cancer cells by making them grow stronger instead of being inhibited. So this was also a very good candidate for synthesis because it was very easily detailed in the paper, so that part was very easy, but it also posed an intellectual challenge because one of the reagents, ferrocene carboxylic acid, I had to figure out how to make on my own. So let's just talk about the broader application of organometallics in medicine. So first of all, through my interview with Dr. Conor Delaney, I learned about the Suzuki coupling, which is a very special type of catalysis that uses a palladium catalyst. And this has opened doors for, I think, thousands of new medicinal compounds. And then beyond just medicine, organometallics are very present in the body. So our blood is composed of hemoglobin organometallic enzymes. One of the most important enzymes in the world, nitrogenase, which fixates nitrogen in plants, has a lot of iron and a molybdenum component here. So it is very important to research these. And then finally, beyond ferrocene-based anti-cancers, there are well-documented anti-cancers like cisplatin and carboplatin that use a platinum center. So let's get into the meat of my presentations. This is my original work and my final product. So for my original work, I created a 4-step synthesis plan to create ferrocene flutamide. So first, I had to figure out how to synthesize ferrocene. And then to get to our carboxylic acid, which was required in the paper for the synthesis, I had to create an intermediate called acetylferrocene. And through that, we could modify this functional group by taking off this methyl group and attaching this hydroxyl group, which allows it to become ferrocene flutamide. So let's look at each of these steps in depth. But before that, I have to talk about my final product. So there are 2 big pivotal challenges and restrictions that really shaped my journey in the lab with Dr. Delaney. So first of all, there was a time constraint. So we only had 20 hours, which is a whole weekend in the lab. So this may seem like a lot of time. However, in reality, we were working nonstop. There wasn't a single moment of rest besides lunch. And even still, we had to modify the synthesis to make it a formal synthesis, which essentially means that we're doing steps in tandem at the same time and potentially out of order just to validate the chemical pathway without taking as much time. And then the most important restriction was actually a legal restriction. So since I'm a minor, I was not allowed to create a biologically active drug, that being the ferrocene flutamide. So instead we had to create an analog that is similar to the compound, keeping the spirit of the synthesis while maintaining legal guidelines. So this is the modified plan that we did for my final product. So these 3 steps are the same, and then of course, this step is different because we had to create a different compound. So this is step 1, this is the synthesis of ferrocene. So this happens in several smaller steps. So first, we have to prepare our hamburger buns, our cyclopentadienes. So at room temperature, it is actually unstable in its monomer form, in its singular form. So it combines itself to create a dimer, which is 2 molecules essentially bonded together. So that's dicyclopentadiene. And so what we had to do was heat it up to cleave these 2 bonds and create 2 cyclopentadiene molecules. So then we had to deprotonate it using potassium hydroxide. So that means taking away a proton, which allows the positive iron cation in the form of iron 2 chloride to coordinate with the cyclopentadienes and create ferrocene. So first off came the dicyclopentadiene cracker. This is the first thing we did. So immediately we first have to open the reagent bottle. So when I open the reagent bottle, first of all, it's this waxy solid. It's like a rubber ball. And it filled the lab with the aroma of sickly sweet and old watermelon smelling bouncy balls. So that was surprisingly pleasant. It was kind of weird. So of course we had to heat it up. So we had it in a flask with, under this oil bath that was heating it up. And then on the flask we attached a condensing column filled with glass wool to increase surface area. So what this does is that it prevents the dicyclopentadiene from coming over before it gets cracked. And then of course at the top here, we have an ice bath. I think it was actually dry ice with the receiving flask. So it was actually very hard to get the dicyclopentadiene to come over, the cyclopentadiene to come over. So first we tried aluminum foil to trap the heat. That didn't work. So we used a heat gun, and that worked marginally, but it still took too much time, and of course we were in a time crunch. So we instead pulled a vacuum, and that brought everything over. So these 2 graphs down here are called NMR spectra. They're essentially the hydrogen fingerprint that proves the structure and purity of molecules. So here we took an NMR of our starting materials. This is dicyclopentadiene. And then after the reaction, we took an NMR of the product. And so this essentially just proves that we did in fact crack the dicyclopentadiene to create cyclopentadiene. So now with this, of course, we have to deprotonate it using potassium hydroxide. So in a flask, we took this clear liquid, the cyclopentadiene, and we added potassium hydroxide. So when we did this, there was actually a color change to this like very brown solution. So this indicated that a reaction was happening. Then we added our iron 2 chloride in a solvent called DMSO. We left it to stir, and so that eventually reacted and created ferrocene. So we got the ferrocene out of the flask by pouring it onto an ice bath with hydrochloric acid. So it acidifies, which reduces solubility, and it also cools down, which reduces solubility. And so with this, we just had to filter it in a vacuum filter, and we got these crude crystals. Now this isn't pure, so we had to purify it using one of the coolest methods to purify something ever, which is sublimation. So ferrocene, when you heat it up, instead of turning into a liquid, it goes straight from a solid to a gas. So we can take advantage of this. Essentially we had a flask, which contained our crude ferrocene, and then a condensing column, which had cold water flowing through it. So when you heat the ferrocene up, it condenses on that cold glass, similar to how ice water attracts water on the outside. And so the pure ferrocene was on this cold glass, while all the tar and all the impurities were left behind here. So all we had to do was scrape it off, and we had these very beautiful crystals. And this is the NMR, the hydrogen fingerprint, proving that it is in fact pure and that it is in fact ferrocene. So now, using using this ferrocene, you now have to acetylate it in step 2. So here's the mechanism. This is a pretty scary diagram. I'm going to break it down for you. It is a acid catalyzed reaction. So first we need to prepare the acetyl group to attach to the ferrocene. So we start with acetic anhydride and phosphoric acid. So phosphoric acid donates a proton to acetic anhydride, which makes it very unstable, so it goes through a bunch of electron motions and eventually splits into acetic acid, which is vinegar, as a byproduct, and then the acylium ion, which is the acetate or the acetyl group in ion form. So with that, it really wants to react with something. So ferrocene comes in, it's like, hey, react with me. So it does react, it makes a bond. However, it forms an unstable intermediate because there's too many protons here, essentially. So the phosphoric acid comes back and takes the proton back. So that recycles our catalyst and creates our final acetylated product for this step. So first of all, we had to retrieve the ferrocene from storage because this was the next day. So essentially, ferrocene is very slightly unstable in the regular atmosphere in air. So it is stored in something called a glove box. So it's under nitrogen, which is an inert atmosphere, it doesn't react with anything. So I had to go in there and feel like an astronaut. I stuck my hands in the gloves and I measured out the amount that I required. It was pretty fun. It was pretty clumsy because the gloves are oversized and the nitrogen kept on pushing me back because it's constantly recycling nitrogen. Also, static electricity was a big problem in there, so the ferrocene kept on sticking to the bottle, sticking to the waiting boat that we used. So Dr. Delaney had me use this magical electron gun. So essentially, it's this gun with a crystal and it shoots electrons to disperse static electricity. I'm still convinced that he was pulling my leg because it didn't really do anything besides just like waving around his magic wand. So there was our ferrocene. So basically, we just put our ferrocene in, dissolved it in a solvent, and we added our acetic anhydride and our phosphoric acid. So when we did this, there was actually a very beautiful color change from the orange ferrocene to this very, very, very deep red. It was the reddest red to ever read. So we let this stir, we react, and then we precipitated it out using sodium bicarbonate, and we filtered it. So originally, we thought that our product was in this flask, this funnel, and all the waste was in the water. So we wanted to purify it using something called column chromatography. However, when we tried to dissolve our product, it didn't dissolve. So this kind of made us panic. So we took an NMR of it, and it happened to be ferrocene. So we thought that nothing reacted, and we wasted a bunch of time. However, in reality, one of my supervisors actually realized that it was dissolved in the solvent, which was very surprising. It wasn't supposed to do that. We didn't even know it was soluble in there. However, this actually made things easier because we just didn't aqueous workup. So you guys know how when you pour water and oil into a glass, they don't mix, right? It forms separate layers. We use this to our advantage. So acetylferrocene is more soluble in something called petroleum ether than water. So we add water and petroleum ether, and then our mixture containing, or our solution containing impure acetylferrocene. And then we added salt to the water, which basically makes it more easily separated from the nonpolar solvent. We shook it up, and then we drained the water layer. And so we were left with acetylferrocene, and all we had to do was evaporate off the solvent. And we're left with these very beautiful crystals. So this is a bigger flask that we used to dissolve it. And so you can't really see it well here, but it was kind of like a stained glass. There's like these needles coming out on the flask. So we redissolved it and then evaporated it in a smaller vial to make it easier to use in the next reaction. And so this is just another reason why I love chemistry. All the compounds that you make are very, very beautiful.
Very clever.
Thank you, Mark. So this is the NMR spectra, the hydrogen fingerprint, that proves that this is pure and that this is really acetylferrocene and that all of our work wasn't for nothing. So our next step is the ferrocene carboxylic acid. So originally I had proposed a triiodation, but this apparently does not work in practice, so Dr. Delaney instead proposed this mechanism. Essentially use sodium periodate, which is a very strong oxidizing agent, if I remember correctly, and it basically just cleaves this part off and adds our hydroxide with some byproducts. So this failed. So everything was going great. We added our reagents, and it was stirring for 5 hours. This was the longest step that we had to do. So it was stirring for 5 hours, and then it was time to purify it. So the paper called for sodium metabisulfite. However, we didn't have this. So one of my supervisors had the idea to use sodium borohydride instead. However, so this would have been fine if we didn't use water as a solvent, but since we did, the sodium borohydride reacted violently with the water, creating boric acid, which destroyed our product, as you can see here. So while we were adding this, we were actually like, wow, yeah, that's so cool. It was purifying our product. And then we took an NMR, and it was just junk. It was nothing. So we had to pivot. So this is the pivot. So instead of using the carboxylic acid, we used a substitute called ferrocene aldehyde, which is essentially the carboxylic acid without the oxygen. And this allowed us to do a separate reaction to create our final product, our analog of the ferrocene flutamide called ferrocene benzylamine. So I'd like to take a quick moment to talk about what we were going to do. So this is from my original work. Me and Dr. Tombar worked on this reaction mechanism together on call. I'm very proud of this. Essentially, we have our carboxylic acid and then an intermediate reagent called oxalyl chloride. So basically, a chlorine atom gets kicked off and it combines the two reagents. And the chlorine comes back in and kicks this whole part off, resulting in a chlorinated intermediate of our reagent, and then an unstable byproduct which decomposes into various gases, which makes purification very easy because everything just kind of goes up into the atmosphere. So after that, we would have taken our, essentially the flutamide part of the molecule. It's called like 4-nitro-3-fluoromethane, or aniline, I forgot the name. And then we use triethylene, which is a strong base. It deprotonates our aniline. And then our chlorinated reagent comes back in, and it reacts, and it creates our final product with chlorine atoms, or chlorine ions as a byproduct. So of course we didn't do this because we didn't have the carboxylic acid. So instead, we performed what is essentially a dehydration reaction. So right here is our two reagents. This is benzylamine, and this is our ferrocene aldehyde. So what happens is that two hydrogens get kicked off of the benzylamine, and an oxygen gets kicked off of the ferrocene aldehyde. So you get H2 and O. What does that make? Water. So it shoots out water, and it combines our reagents, making our final product. However, this is a reversible reaction.
Are we allowed to drink the water?
I would not. You might die. So, this is a reversible reaction. So if water is still present in the system, it can re-react and split up the reagents again. So this is bad, obviously, for yield, because we wanted as much as the product as possible. So we used magnesium sulfate as a drying agent. So it pulled out the water and let us continuously create our final product without it reversing. So this is a quick overview. We got a reagent, which looks like Cheeto dust. It's actually a pretty beautiful orange. Then we added our reagents, we stirred it, heated it up. It was very quick, thankfully, because we were almost out of time here. We were almost out of time. And then we simply filtered it out. And so this is our product in the solvent. And so we had to perform an aqueous workup again. So remember, water and a nonpolar solvent, same thing, petroleum ether. So this is actually kind of risky because when you add water into it, remember this splits up our product into our reactants. So this could reduce yield. So I had to do this as quickly as possible. So I added everything. I shook it up real nice. I drained out the water as quick as I could. So we were left with our product that we dried in a rotovap, which by the way costs something like $100,000 for something that dries things really quickly. So this is our final product. I was actually expecting crystals to come out of this like the other steps. However, it was this red oil. This is a very interesting red oil. It refused to be picked up by any of the pipettes we used. So So we would suck it up and it would just fall out. So it was kind of frustrating. However, this is very beautiful in its own way. It's very oily, it's very red, and it stains everything. But it was mine, and I was very proud of it because I spent 20 hours making it. So that was my final product. Thank you all for coming. I'm going to open the floor for you guys to ask questions. Welcome, Jack.
Did you bring it with you?
They didn't let me take it.
Oh, I thought you were gonna wear it on the chain around your
No, I wanted to wear it on a chain, yeah. Yeah, they didn't, well, I asked my mentor and he said that they would have his head if I took anything home from it. So, yeah, I really want some Ferris to take home, but I'll just have to make it myself in my garage.
Be careful of that, Jack.
I'll make sure it's well ventilated. Does anyone have any questions? Or is that it? Did I do too good of a job?
I think it's.
Yeah.
Welcome to my world, Jack.
I'm staring at a blank space.
Good job, bud.
Yeah, thank you guys so much for coming. Thank you, Dr. Tombar, for being here, for being my mentor.
Yeah, thank you.
You did a great job explaining things. That was good.
Yep, thank you.
That's not an easy.
Guys, don't forget the Christmas chairs.
If you guys haven't already, you can take a program as a souvenir with the brochures outside the door. Feel free to take more food so we don't have to take it home.
I'm mother of Harish. I don't know if you heard his name. He did his biochemistry in UTD. And he went to UT Southwestern for the SERV for green scholars.
You worked for Miles.
Yeah,
He's
he's doing good. He's at UC Berkeley. He's the one who connected you.
Oh yeah. No, I remember him really well. Yeah. Well, Berkeley's such a great school. So actually, this guy that he worked with at UT Dallas, he used to be at Berkeley also.
Oh yeah, nice.
So,
Yeah,
Thank
he's
you for coming.
enjoying it over there. Nice meeting you.
No, it's very nice meeting you. Yeah. That's great.
He did great.
Yeah, he did really
Harish
good.
doesn't talk. He never tells you that details. So,
Yeah, he did great.
yeah.
Yeah, he did
Ryan,
great.
I